Okay, thank you. Thank you for coming, and it's an honor to be here. Okay, so this is sort of the short version of the title. The long version is macroscopic scalar curvature and minimal hypersurfaces, although in some sense, macroscopically minimal hypersurfaces will happen in the second half. So first I say something about what is macroscopic scalar curvature. So that's based on the idea that scalar curvature is related to the volumes of infinitesimal balls. So if you have greater scalar curvature, corresponds to lesser volumes of infinitesimal balls. And so the analogy is that greater macroscopic scalar curvature corresponds to lesser volumes of unit balls. And throughout, I'll be talking about that we're in a manifold with some Riemannian metric. So in that Riemannian metric, we can say what unit balls are, and we can say what their volumes are. So macroscopic scalar curvature is more a keyword that we put in titles of papers rather than something that has an actual definition, because what it means sort of varies from theorem to theorem. But yes, so first, so the theorems in the talk are sort of divided into two different kinds. One kind is the ones that are about positive curvature, and one kind is those about negative curvature. So in order to say what I mean by that, I'll give an example of something familiar about surfaces. So suppose that we have closed-oriented surfaces. And suppose that we know that curvature at every point is greater than 1. Then from the Gauss-Bonnet theorem, we automatically know what that means, that our surface is a sphere, and it's kind of a small sphere. The area is smaller than that of a standard unit sphere. And if you didn't know this, but you just knew the curvature is greater than -1, then you wouldn't have any restrictions on what the topology would be. But if you know that you have genus at least 2, then you know something about how the area compares to a hyperbolic surface. So area is greater than that of a hyperbolic surface of the same genus. So I'm going to have some theorems that look, or statements that look like this first version, which I'll say is the positive curvature version, and some statements that look like this second version, the negative curvature version. In both cases, the hypothesis says like a lower bound on curvature, which corresponds to an upper bound on volumes of balls, but the conclusions are in two opposite directions. One of them says the area is less than something, and one of them says the area is more than something. Yeah.
So are you assuming some assumption that breaks the scaling? Like total area is equal to, I don't know, does curvature larger than 1, right? That is, I don't know, you can rescale everything and...
So the scaling ends up in here with what you're comparing it to. So you're comparing the area to a standard unit sphere, or comparing it to a hyperbolic surface of some genus. So hyperbolic meaning that it's locally isometric to hyperbolic space, which doesn't emit scaling. Yeah, unit sphere and yeah. Okay.
So summarizes the topological conclusion that doesn't need 1, but would be true with larger than any positive constant.
Right. So in the hypothesis, curvature is greater than some positive constant or some negative constant. Yep. Okay. So the main theorem will be about negative curvature, but I wanted to start off with sort of like a demo problem in positive curvature. This is in 2 parts. So for this positive curvature statement, you can immediately say, well, is there a macroscopic version of this theorem? So suppose that we know we have a surface where the unit balls in the surface have a very small area. Then do we know something about saying that the area of the whole surface is not too large? And the answer to that is no, because you could imagine a sphere with a Riemannian metric where it's very long and skinny. So this is S2, where every unit ball has small area, but the total area is large. And that's because if you want to look at a unit ball, the ball around a particular point is going to be all of the points where you have a curve of length at most 1 to that, and it looks really a lot like a thin cylinder, and so it has a small area. But the problem there, so the reason why this is different from what we have over here, seems to be that the cylinder is very flat looking and yet still has a small area. So what I thought is, well, what if we take the universal cover of that cylinder and we unroll it into a big strip? Then the balls in that strip do not have small area. They have Euclidean area. So that's the question. So can we have, we want to strengthen this hypothesis about the balls. So look at what I wrote. I'm going to use as notation B tilde is going to be the universal cover of a ball of radius 1 around a point P. And then I want to suppose as the hypothesis that the area of a ball in this ball around a lift of P is small, and that this condition is true for all points P. My surface is going to be called sigma. So can we have this condition on balls, but the area of sigma is large. So the answer to this turned out to be no, that this was the modification that we need on the hypothesis in order to get a theorem that looks like this one. So I wanted to give part of the proof of this statement for various reasons, to give some flavor with something very concrete, and then also because it brings up some other questions that I wanted to talk about. So we're going to break it down by talking about the diameter. So I'm going to start with the case where the diameter is at least 2, and then address the case where diameter is less than 2. Actually, when we do this first case, it'll turn out this is impossible, that if you assume this is true, you get a contradiction, and then you're in the second case. But so for this case, we pick 2 points of distance exactly 2. Oops. And find a path of length 2 between them. And the point P that we care about is going to be the midpoint of this path. And we're going to show that we have a contradiction with the balls around that point. So this is going to be a picture of the ball in the universal cover of the ball around P. So we have the lift of P, the lifts of x1 and x2. And this curve going up and down is supposed to be gamma, the minimizing geodesic. I drew the ball really long and fingery like this because we know it has to have a small area despite having radius 1. So what I'm going to do is look at the balls of smaller radius around this point and look at the boundaries of those balls, the loops that are the boundaries of those balls, sort of sweeping out the disk. So for t less than 1, let S for sphere, pt be the loop enclosing the ball around p tilde of radius t. And this step is actually where we're using the fact that we took the universal cover. Otherwise, in some arbitrary metric, your ball may have sort of terrible topology, and its boundary may have several different components, and so on. But in our picture, because we took the universal cover, even though the boundary may have several connected components, there's one of them that sort of encloses all the rest. So that's the loop that we're going to care about. And then what we have is co-area inequality implies that if you integrate the lengths of these, you get something that's nicely bounded. if we integrate from t equals 1/2 to 1, then we get something that's at most the area of that sort of annulus that sweeps out, which is at most the area of our whole disk. Which is at most epsilon. So there is some t between 1/2 and 1 such that the length is short. Less than 2 epsilon because we're integrating over an interval of length 1/2. So this, I could say, is and then this loop that we've now found provides a shortcut for how to get from x1 tilde to x2 tilde without going through p tilde. So replacing gamma from, I guess I should label these intersection points, x1 prime and x2 prime. From x1 prime to x2 prime by s p tilde t reduces length contradiction. So then that concludes the case where diameter is at least 2. And then I'm actually not going to do the other case. So I'll just write here, case diameter is less than 2. I'll claim this is sort of more tedious and really just less relevant for my talk. You basically start at one point and then grow outward, and after covering by like 8 different balls, then you've exhausted your surface, and so it doesn't have a very large area. Yeah. So yeah, so I was claiming that the area was small, but actually here it's the diameter is also at most 2.
So the actual ball is like some constant times actually? If you try just the word just by the diameter?
Yeah, I think it was just 8 times epsilon as long as epsilon is less than 1/8, something like that. Okay, so one reason I wanted to go through this is so that I could talk about a conjecture of Gromov. Which was about, well, stated in terms of scalar curvature. So it says if an n manifold M has very positive scalar curvature, then M can be mapped to an n-2 dimensional simplicial complex such that every fiber of the map, the preimage of each point has small diameter. So So the image that you should be thinking of here is that M might locally look like a small two-sphere cross Euclidean space. Then we would be sort of projecting to the Euclidean space part, and then 2 dimensions for the sphere would go away, and those 2 dimensions all you need to have the positive scalar curvature. So let's see. So if M is 2-dimensional, then we have the positive curvature statement that I said at the beginning, that that your surface is a sphere that's pretty small. Okay, so as far as I know, this is not known, how we might prove this. So one question then, and it's not even known if we replace n-2 dimensions by n-1 dimensions, which should be a strictly easier thing to prove. So then you could ask what happens if we replace this positive scalar curvature by an assumption about volumes of unit balls. So if M is a surface, that would be saying that if all of our unit balls have very small area, then we look something like this very skinny sphere, or maybe like we took the small neighborhood of some one-dimensional simplicial complex rather than just this path. And then if you map the surface to that one-dimensional complex that you were thinking of, that would be the map to an n-1 dimensional complex that has small fibers. So this statement for all n, and where we replace this n-2 by n-1 and put a macroscopic hypothesis, that was proved by Larry Guth, my advisor. I'll be talking about a bunch of things that he's done. But the question of how you would get a statement for n-1 instead of n-2 and with a macroscopic scalar curvature hypothesis is something that we have been working on and I'm interested in continuing to work on. So that was one reason I wanted to talk about this conjecture and the demo problem. So I think that's the end of the positive curvature introduction, and I can go on to saying things about negative curvature problems. So for negative curvature, I wanted to draw sort of a cartoon picture of what the theorem statements are all going to look like. This is supposed to be a very big genus 2 surface. And if you were to take a unit ball in this surface, it would look only a little bit curved, and so mostly like a Euclidean disk. Whereas if you took a really small genus 2 surface and you took a unit ball, well, in this case, the unit ball might cover most of the surface. So that's actually not what we're going to do. We're going to start by taking the universal cover of this very small surface and then take a ball, which will be very negatively curved. So if I draw it, I don't know, very wiggly to try to look negatively curved. And we're doing balls in the universal cover. So this second ball has a much bigger area than the first ball. And the theorem statements are going to go in this direction, or equivalently this direction. that either if we know that the balls are not too big in area, then the whole manifold is big, or if we know that the whole manifold is small, then there exist balls that are big. Okay, so the first theorem that I know of that follows this history is what I'll call the Entropy Theorem. Which is from Gromov in the paper Volume and Bounded Cohomology. So it goes as follows. Suppose we have M is a closed n-dimensional manifold admitting a hyperbolic metric and suppose that G is some arbitrary Riemannian metric. Well, it's not, we're going to have hypotheses, but it's not necessarily hyperbolic. Then it's going to look like the top row cartoon picture. So we're going to, no, it's going to look like the bottom row cartoon picture. We're going to assume that the whole volume is kind of small and get that there exist balls that are kind of big. So suppose that the volume with respect to G is smaller than a particular constant depending on M times what the volume would be under the hyperbolic metric. Then for all sufficiently large radii, so for all r greater than some constant r naught that depends on M, there exists a point around which the ball of radius r is big. So P tilde in the universal cover with the volume of the ball in the universal cover around this point. The ball has radius r is bigger than what you would get for a ball of that radius in hyperbolic space. So I'm writing the ball around any point in hyperbolic space because all those balls are isometric. So this theorem is only for sort of sufficiently large radii. A more recent theorem says something that's almost the same as this, except we replace the very large radii by radius 1. So I'll call that the unit ball theorem. And that's from Larry Guth, published in 2011. I'll say, also, there exists P tilde with the volume of the unit ball greater than the volume of this hyperbolic space unit ball. So in particular, I didn't say we can take R naught to be 1. That statement is not known how to prove that, although it seems to be true, and it's a conjecture that I am interested to work on. So the reason why this subtlety exists, it comes down to this constant here. We might want to use a different constant depending on n for this first theorem and for the second theorem. And the second theorem says that for any radius that we pick, there is some such constant, but for the intermediate radii between 1 and infinity, the constant may get very bad in a way that depends on the manifold and not just on M. So trying to prove that that does not happen would be the conjecture that's stronger than this that I would want to work on. So I was learning, yeah?
I'm confused about the inequality. So what happens if you just scale the hyperbolic metric down? I mean, you're saying that it's less, but then here it's bigger.
Yeah, so if you took the hyperbolic metric and you shrink the manifold, then you'll get this hypothesis, and the volume of balls in the universal cover will be big because they're much more negatively curved. Okay, so I was learning about this unit ball theorem and its proof, and Larry suggested trying to prove something that's like this, except for hypersurfaces in the manifold. So suppose that we knew that our manifold is diffeomorphic to a hyperbolic surface cross S1. Then the picture that we're thinking of is something like this, where sideways is the S1 direction, and sort of every fiber looks like our hyperbolic surface. Then for a theorem statement, we would replace this hypothesis about the total volume of the manifold with one about the total area of the surface. So we want to say if some copy of sigma is really small like this, then we can find some ball in the universal cover of the whole manifold, probably somewhere around here, where it looks very negatively curved, and thus the ball has a very big volume. So a theorem like this was known for just scalar curvature rather than macroscopic scalar curvature. I'll call it the old hypersurface theorem. And I'm not actually sure who first stated and proved this theorem, but I know it's based on the strategy from Shane and Yao in 79. So this theorem I'll state in terms of a closed 3 manifold. And looking for minimal surfaces. So suppose that we have H is a 2-dimensional stable minimal surface. and I'll say it's connected. And then I'll say SC means scalar curvature. If we have a comparison between the scalar curvature of our manifold and that of hyperbolic surface cross Euclidean, so suppose the scalar curvature is less negative, so greater than that of hyperbolic plane cross R, then we conclude that the area of H is greater than, H with our current Riemannian metric is greater than the area of H with its hyperbolic metric if the genus is at least 2. And the theorem doesn't say anything if we have an H that has a smaller genus. So the main theorem is very much like this, except with scalar curvature replaced by macroscopic scalar curvature. One feature of this version of the statement that wasn't true for the main theorem when I first proved it with K Funano is that we don't assume anything about M being a product. So I had an earlier version where M has to be a product, but in order for it not to be a product, in order to have a conclusion where we're comparing the area of H with something about the topology of H, I'm going to be using the Gromov simplicial norm. So I want to say very quickly how that's defined so that I can use it in the theorem statement. Okay, so the Gromov simplicial norm is a function denoted by norm with a triangle from homology with real coefficients of any topological space to non-negative numbers. And it's based on taking the L1 norm of our cycles. So if we have a singular chain where the sigma I are simplices and the alpha I are real coefficients, then we say that the norm of this chain is the sum of absolute values of coefficients. And then if you have a homology class H and you want to take its simplicial norm, then we take the infimum over all cycles C that represent it of the norm of that cycle. So the sort of motivating property of Gromov's simplicial norm is that in the case where you have a hyperbolic manifold and the homology class that you're taking the norm of is the fundamental homology class of your manifold, then what you get is proportional to the hyperbolic volume. But then its other properties are, it much generalizes this, and it has good properties under continuous functions and stuff like that. So now I should be able to state the main theorem. Okay, so I have my closed Riemannian N manifold. I have some n-1 dimensional embedded hypersurface. And I don't need to assume anything about area minimizing, mostly because I'm going to be looking for a lower bound on its area, and so that'll imply this statement for it not area minimizing. And then I'm trying to figure out if I have enough board space. Board management. Okay. Okay. Suppose that we have this analog of scalar curvature bound for macroscopic. So suppose for all points p tilde in the universal cover, we have that the volume of the ball of radius 1 is not too big compared to what we would have in hyperbolic cross Euclidean. So h n-1 cross r. Then we have our conclusion that says that the area of H is at least something. And the something here is going to be a constant of n times the simplicial norm of the homology class corresponding to H. So here, what I'm writing is, say that we have I denotes the inclusion from H into M. Then we take the fundamental homology class of H in the homology of H, map it to the homology of M, and take the simplicial norm there in homology of M. And that's going to be our lower bound for the area of H.
What are the assumptions on H? I guess you need stable minimum or something like that.
So, right. So for H, if you prove the theorem for saying that H is almost area minimizing, which I'll sort of be talking more about later, then you get this bound, and then knowing this bound for such H implies it for any other H, which will only have a larger area.
Okay.
I did, I guess, forget another hypothesis, which is mostly technical. Assume that the fundamental group of M is residually finite. But yeah, if we knew that M was area minimizing in its homology class, that may help us prove more things, and then it will also imply this same statement for any other things in the
But
homology
how
class.
about the tiny geodesic ball? I'm a little bit confused about. You know, take the epsilon sphere around the point, right? as your H.
H would be 0.
Right, so this simplicial norm is often 0, and it will certainly be 0 if this homology class is 0. Yeah.
So in some way, the non-triviality of H is encoded in the right-hand side there.
That's right. Yep. Okay, so so before saying more about how this theorem is proved, I wanted to say a little bit about positive curvature, because when I told this theorem to Andrea Neves, she asked me, is there a positive curvature version? So one example of what a plausible positive curvature analog of this would be, suppose that we know M is diffeomorphic to a two-sphere cross a circle, and we want to know if we know that the unit balls in the universal cover are small, then we want to know, must some copy of S2 be small? Rather than big. The answer to this formulation is basically the same as what I said at the beginning with the very long and skinny S2. If you take that long skinny S2 and you cross it with a large circle, then you do actually have every copy of S2 has a large area, but also your unit balls look like a very skinny cylinder across Euclidean and thus have a small volume. So in that sense, it's no. But of course, in the positive curvature demo problem, I modified the hypothesis so that we're looking at universal covers of balls. But it turns out that I made a construction suggesting that even if you do that, the answer to this is still no. So I'll put up that example. Or at least a picture sketching the example that I came up with. Okay, so the example is there exists a three-manifold M with volume of balls in the universal cover of balls using the same notation I introduced before, are all small. I guess that's just not right. I wanted P. But M has a stable minimal surface H of large area. So I'm going to draw M by mapping it to a circle and drawing what the preimage of each point is. So here's my circle. And this point is going to have a preimage that's my special h, and it's going to look just like that long and skinny S2. If we were to have that going all the way around, we would have a problem with this. But the way I'm going to deal with that is I'm going to put fibers next to it so that these short loops can be null homotoped nearby. So what's going to happen is that this long and skinny sphere is going to pinch into many much smaller spheres that are all going to be disjoint. So this is sort of the singular version. Then we get this, which goes all the way around for most of the circle, and then comes back symmetrically on the other side. So the property that this has is going to be that when we take the unit balls for the first time, they're going basically to be simply connected, and so taking their universal cover before taking the unit balls a second time isn't a step that actually changes anything. So the property is that every small loop is contractible in a unit ball. So that's this construction, which suggested to me that I didn't think that there can be a positive curvature version of the main theorem. So after the break, I'll talk more about this main theorem, how you prove it, and different versions of a macroscopic stability lemma that talks about how the macroscopic scalar curvature of a whole space relates to the macroscopic scalar curvature of its area minimizing hypersurfaces. So the main theorem, one piece that goes into it is what I wrote as the unit ball theorem here, which will be applied to the hypersurface H. That will give us sort of the conclusion saying that H has at least a certain area. But in order to apply the unit ball theorem, we need some information about the macroscopic scalar curvature of H, whereas we're starting with only a hypothesis about the ambient manifold M. So to get between those, we use different versions of what I will call the macroscopic stability lemma. So I'll start by stating and proving that. And this is from Larry Guth in 2010. So it says the following: if we have an n-dimensional Riemannian manifold, and suppose we have a cohomology class in dimension 1 with z mod 2 coefficients, and suppose that this cohomology class has length at least 2, meaning that every loop gamma, where alpha evaluates to a non-zero number, has length greater than 2. Then we have a relationship about balls in a hypersurface dual to to alpha. So if H is an n-1 dimensional embedded hypersurface, dual to alpha, and I'm going to say area minimizing up to delta in its homology class. So here, dual to alpha means that Z mod 2 intersection number of loops with H is the same as evaluating alpha. Area minimizing up to delta means delta is a small number and the area of H is within delta of the infimum for all embedded hypersurfaces in its homology class. Then we get the conclusion. Then we look at the part of H that's in a ball around P and compare that to the volume of a ball around P with this inequality. So the proof is pretty quick, especially because I already foreshadowed it with the positive curvature demo theorem proof, which is based on this one. So for the proof, we suppose not and look for a contradiction. So what we want is to find for some t between 1/2 and 1, we want to replace the part of H that's in the ball of radius t by something that's homologous to the original, contained in the sphere of radius t, so SPT, which will be as before the boundary of the ball of radius t. And it should decrease area by more than delta. So if we can decrease area by more than delta, we'll get our contradiction. So here's my picture. So this is my H. And so basically what I'll have is I have H, there's this part of it that's in the ball, and that part I'm assuming is too big. And I want to say if that's the case, then I can replace it by adding or subtracting the boundary of this shaded region to replace it by this other part that's part of the sphere. So that H just goes around the ball. And then we'll have a smaller area. So in particular, as in the earlier proof, we select the T using co-area inequality. So we pick T such that the area of the sphere has at most average area. So we have the area of the sphere is at most 2 times the volume of the ball. And what we've assumed is that this is less than or equal to something involving H. So we assumed for contradiction the following. This, I'm just negating the hypothesis. And then this is at most the same thing with 1/2 replaced by T. So because of this, the numbers work out that it suffices to find well, I'll say show that the part of H that's inside the ball of radius T is homologous to something contained in the sphere. Because then its replacement would have area at most this, which would be dropping by at least delta. So now let's do the second part. Okay, so this second part about showing there's something homologous is where we use the hypothesis about length greater than 2. So the fact of length greater than 2 implies that every loop in a ball of diameter at most 2, in particular BPT, has a 0 mod 2 intersection with H. The 2 factor is from integrating along an interval of length 1/2. So the average area from this inequality is at most 2 times the right side. Okay, so for this statement, there's a little bit more detail that you could say here, involving taking a loop that may be longer than 2 that stays in this ball and breaking it up into shorter loops, but this is true. And so that means, or that's equivalent to saying that we can 2-color the components of the complement of H. So by 2-color, I mean we have this ball, it's broken it up into connected components of the complement of H. Each connected component gets one of the 2 colors, and if they, if 2 of the regions share a boundary that's part of H, then they should have different colors. But then once they're 2-colored like this, we can select one of the colors and take the boundary and modify H by that boundary. So we add the boundary of the first color to H, and then the effect is we replace the part of H in the ball by something on the sphere. And again, this depends on the mod 2 coefficients. The boundary of the first color includes everything in H inside the ball exactly once. And so that exactly cancels out mod 2, the part of H that's inside the ball, and the rest of the boundary of the first color is going to be on the sphere. So later I'll be talking about sort of different versions of this where we change different things, and then the proofs are going to be sort of similar to this. But this version allows us to prove an easier version of the main theorem, which I will now state. So in this version, I will assume that M, our manifold, is a product the product of a hyperbolic surface with a circle. And then I'll have my assumption about the macroscopic scalar curvature. Then, instead of an arbitrary hypersurface, I'm going to talk about a surface isotopic to sigma, my sigma factor. For any sigma prime in M isotopic to sigma, area of sigma prime with respect to our Riemannian metric that we have is at least a constant times the hyperbolic area of sigma, or of sigma prime, which are the same. Actual bounds for the constants, let's see. So because this is based on what I called the unit ball theorem, I think the constants there are not good at all. I think you could have constants, but they wouldn't be good. Okay, so the proof sketch, which is sort of just an outline, the strategy is to find some surface we can compare sigma prime to, so H that's in the same homology class as sigma prime that's minimizing up to delta. And then we apply the lemma to H to get that the balls of radius 1/2 in H are not big. Then we apply the unit ball theorem to H to get that the area of H is at least a constant times, I'll say, the hyperbolic area of sigma. For these things that are in terms of hyperbolic area or volume, the proof is always done using the Gromov simplicial norm, so I always am sort of deciding which one of them I want to say that would be clearest. Yeah, the proofs are all with Gromov norm. So that's the strategy, but we need to say a little bit about why we can apply this lemma in relation to this length greater than 2 hypothesis that we need to use it. So, how to get the length greater than 2 hypothesis for the lemma. So I'll try to draw a picture to show what's going on here. Here's M, and it's a surface cross a circle. So I'll say the circle's going this direction. And I'll say that this copy of the surface is my sigma prime. If the circle direction is too short, then we cannot apply the lemma directly because the cohomology class that we're talking about is the class that's in the direction of the circle factor. So if that's too short and is length less than 2, then we need to take covering spaces. So I'll say MD will be the cover of multiplicity D, where we unwind the S1 direction sort of D times to make it really big. So what that looks like is much longer. Looks kind of like this, and then all these that I drew are the copies of sigma prime, isometric copies. So then, well, I guess I can fit the one sentence that I was going to write here, is we take H in this M sub D, homologous to sigma prime, and then apply the lemma in MD, which now, if D is large enough, has the right length hypothesis. And so that concludes the proof sketch for the easier version of the main theorem. So we proved this version and then immediately wanted to know, does this work if we replace isotopic by homologous? So I'll show how if we try the same proof, we might get a problem. The issue happens if sigma prime connects to itself in a way that goes around the circle direction. So this is sort of hard to draw, but suppose that it goes like this and all the way around the circle and then sort of comes back to itself. By adding the boundary of sort of a very long rectangle strip. Then, when we try to take the cover, the preimage of sigma prime is going to be connected. So it's going to look like we have all these connections. Now my picture is going to look terrible, but so the problem is preimage of sigma prime in MD may be connected. And so then, okay, what happens if we keep trying to to do the same thing, because of the z mod 2 coefficients, we care if d is odd. So let's say d is odd, that's fine. We don't have a problem with that. But then let's look at the homology class corresponding to this preimage. I'll say pi is the name of the map. The preimage of sigma prime is going to be d times the homology class of sigma, which with z mod 2 coefficients is homologous to sigma. And then if we take h, that's area minimizing in MD, then we get something, but it's not what we want. So we get the area of this preimage is at least the area of H, which is at least a constant times the hyperbolic area of sigma. But this left-hand side is d times the area of sigma prime, and there's no way to really, it seems, to get around the fact that we have this large number d on the left-hand side and no d on the right-hand side. So that the issue is, what if we had a weird situation where somehow we were able to have area of sigma prime is less than the area of H, so that the area minimizing hypersurface in the cover is like bigger than the area minimizing hypersurface in the downstairs for some reason. So this didn't seem to work. So no. So then we were trying to get different versions of the stability lemma that would work around this issue and try to make it so that we could prove something like this, except replacing isotopic by homologous. So we were trying to get a version of this where we can eliminate this length assumption on alpha. So for simplicity of stating the lemma, I'll say M is diffeomorphic to a product. Sigma cross S1. I'll say H is an embedded hypersurface homologous to sigma. And minimizing up to delta. Then, to state the conclusion, I want to define notation. We'll say M sub infinity is like MD, except you take D equals infinity. It's the covering space it looks like sigma cross r from unwinding S1 all the way. Then the conclusion says for all p in M, the left-hand side is the same. But now we're taking a ball in M infinity instead of the ambient manifold. So this one is in M, and that one's in M infinity. So if we didn't make this modification replacing ball in M by ball in M infinity, then the statement would not be true. So that's my note. Suppose we had sigma is very big, so nearly flat. Sigma and cross tiny S1. Then this is a case where you actually care that we have M infinity here, because the volume of a ball in M of radius 1 is small. It looks like two nearly flat dimensions cross a really tiny S1, so its three-dimensional volume is small. But the left-hand side is not small. Imagine H looks like sigma, it's nearly flat, and so this looks kind of Euclidean. But fortunately with the fix, this is fine. The ball in M infinity is also not small. It looks pretty Euclidean because we unwound the really tiny S1. Okay, so this version is more complicated and confusing to prove. I'll try to draw simplified pictures and say that that's some idea of the construction. So the overall proof structure is going to be the same, that we're going to pick a good radius t and look at the ball of radius t and its boundary. So if I take, pi being the covering map, if I take the pre-image of a unit ball, or I guess here I have my ball of radius t, then in the universal cover, it's going to be the union of z many balls. As in the following picture. So here's my one lift of my point P, and I'll call it P0. And here are some other lifts of P. And here's my ball around P in M infinity, the preimage of that ball downstairs is going to be something that looks sort of like a scallopy strip. Going off on both sides for z copies of like translates of this ball. And I'm going to label the lifts of P by the integers. Okay, so the construction is we find our T with the area of the sphere in M infinity small. And then we try to replace the part of H that's inside the ball of radius T by the following somewhat confusing thing. So first, I look at this strip and I look at just the half that's the union of balls of P at least 0. So I take this set, this half strip, then I take the boundary, and I'm taking the boundary in relation to the whole twice infinite strip. This is I. So the boundary of the half is going to be this side of the of my P0 ball. But in general, these balls could be much stranger in relation to each other, and this boundary may have parts of the boundaries of many copies of the ball, not just the 0 one. And then this is going to be some surface of the correct dimension, but in M infinity, and we need to send it back down to M. And when we send it back down, we need to keep track of the Z mod 2 multiplicity. Okay, so this is the construction that I claim is going to give us the right thing. And what we would need to check in order to do the proof is that this is actually homologous to what we started with. So in particular, every loop in the ball in M of radius T has the same mod 2 intersection with this as with H. And I'm not going to say what we do to check that. But I claim that you do this checking, and then that would be the end of how you prove this. So So this gave us the version of the main theorem where we do have homology instead of requiring the surfaces to be isotopic, but in our version here, the ambient manifold M was still a product. So to get the version of the theorem that I stated originally, where we don't need M to be a product, but just measure the area of the hypersurface in terms of its own topology in M, I wanted to get the version of this macroscopic stability lemma with integer coefficients on homology rather than Z mod 2 coefficients. So the integer version goes as follows. Suppose we have our manifold M, and we have a cohomology class in degree 1 with integer coefficients. And suppose that has length greater than 2. Then we have H is our embedded, oriented hypersurface, dual to alpha and minimizing up to delta. In its Z coefficient homology class. Then for all points P in H, we have area of the ball in H around a point P with radius 1/2 is at most 2 times the volume of a ball in M of radius 1 plus delta. And you notice that I replaced this left-hand side. It used to say H intersect a ball in M. So this one would be false if we replace this left-hand side by the other left-hand side. Because we could look at homology classes that require H to have many parallel sheets inside this ball. So if H looks like D times sigma, for instance, maybe it has D parallel sheets. Then, if D is large, then the left-hand side would be big and the right-hand side would not be any bigger. So what happens instead is that if we take the ball in H, then we only get one connected component of these many sheets. So B taken in H, P of radius 1/2 is part of the connected component of the intersection of H with the ambient ball, the connected component containing P. So the proof of this integer version, even though it took us longer to formulate and think of how to prove, turns out to be easier to say. So the outline is the same as before. We say suppose not, and we find a T such that the corresponding sphere has small area. And then here's a picture of what happens. So here's our ball, and here's sort of H going through. And I'll call this first connected component that contains P H naught, but maybe there's some other connected components of H going through. And then I'm going to break the ball into sort of layers according to the parallel sheets of H. So the complement of H is being labeled with integers in the following way. This part is going to get sent to 1. This part is going to get sent to -1. And we continue with the odd numbers. And then so that we can label the in-between parts with the even numbers. And the rule here is that if you have 2 points and you subtract their layer numbers, that should correspond to the intersection of a path between the points with H. This is 2 times intersection number with H of a path Q1 to Q2. And then what we do is for each of these H levels, we look at what would happen if we pushed it through a bunch of layers to get to any of the other H levels, and select to push it to the one that has the least resulting area of that level. So H naught, we compare it to what we would get if we pushed it past here to get H2 plus this bit of the sphere. or if we pushed it up more to get h4 plus these bits of the sphere, or if we pushed it all the way up to get this half of the sphere. And take the infimum of those, and that will be our replacement. I just don't want to go over time, otherwise I would write it out. But yeah, using these layers, you can get a way to get the replacement that makes the level work. I think that's all. Thanks.